So welcome back to the second module of the second week of getting started with competitive programming, and we continue our journey through problems that require some application of either sorting or searching, and in this video it's going to be searching. So we will be talking about a Codeforces problem from round number 403, and the problem name is "The Meeting Place Cannot Be Changed." And it turns out this is also the title of a 1979 Soviet 5-part television miniseries, so that's information that you probably didn't need to know. But that's what shows up when you do a Google search for this phrase. So if you want to get to the Codeforces problem statement, make sure to add Codeforces to your search query or just use the link in the description of this video. So this problem has a pretty short story, but I will say that the binary search aspect of the solution was not very obvious to me from the outset. There are some problems where from the statement you can quite easily guess that there must be some kind of a binary search involved here, but I will say that in this one, at least to me, it felt a bit hidden. It seemed like the statement was suggesting more of a greedy sort of an approach or something like that. But of course, once you start thinking about it and you look at the problem limits, it becomes clearer and clearer that you have to do some sort of a binary search. So let's get started by looking at the problem statement as usual. So it all starts with this road in Byte City, which can be thought of as a straight line that goes from west to east. I should point out that this is not verbatim from the problem statement, where it's a north-south road instead. But I wanted to give myself some horizontal space on these slides, and I did not also want to disorient you by calling this horizontal line a north-south road. But this detail is really not relevant to the main mechanics of the problem, so I just wanted to flag that it is different, but it does not matter. So this road is demarked by integer coordinates, and what we are told is that there are n friends who are standing on this road. In fact, we are given their exact locations as input as well, as we will see later. And we are also told that these people can move around on the road in either direction, and each individual has a maximum speed that they can travel with. Okay, so you have n people standing at these n locations, which may or may not be distinct, and each one of these people has a speed with which they can travel, and they can travel either towards the east or towards the west. Okay, so what do we want to do? Remember, the name of the problem is "The Meeting Place Cannot Be Changed," so you might guess that the problem itself has something to do with getting these people to meet. And indeed, it turns out that the question we want to address is, what is the minimum time that we need for getting all of these people to meet? By asking them to move, of course, if necessary. So we can direct, the first person, for example, to go eastward, the second person to go westward, whatever we want them to do, we can just ask them to do it. And we want to know what is the most optimal set of directions that we can give these people so that they come to a common point after a certain amount of time has lapsed. And we want this to happen as quickly as possible. So that's the question. And also, one thing to note is that the place where they meet, it's not constrained to be an integer coordinate. So they can meet anywhere on this line as long as they get to meet. And that's what's important. Okay, so let's maybe work through an example. As usual, we will pick up one of the sample inputs and go over it. So these distances or these coordinates are measured from the eastmost building. So we just think of this building here as the origin, and we have coordinates being given as distances from this origin, right? And here is the first sample input. What we have is 3 people who are standing at locations 7, 1, and 3, and their respective speeds are 1, 2, and 1. So let's highlight those as well. So you can see that the speeds here are color coded according to the people who have those maximum possible speeds. And at this point, maybe you want to work through this yourself. What is the smallest amount of time that you will need to get these people to meet up at a common point? So please take a pause here and try to figure this out without hopefully looking up the problem statement, because this is a nice example to actually work through. It'll hopefully give you some intuition for what's going on. Okay, hopefully you had a chance to think through that. So let's ask ourselves if, for example, if 1 second is enough. So here is the scope of how much people can travel within 1 second based on their speeds. Okay, now you can see that the green and the blue intervals are disjoint. So even if the green guy comes as much to the right as possible and the left chap moves as much to the left as possible, so both of them are stretching as much as they can, it will still not be possible for them to meet. Okay, so we know that 1 second is not enough. So maybe we want to ramp this up and try to work with 2 seconds. Would that work? Again, if you haven't completely worked through the example already, this is another chance to pause and try to figure this out. Okay, so with 2 seconds at your disposal, notice that people can move around more, and you indeed have a valid meeting point at the fifth coordinate. So in particular, you could ask the green point to move 2 steps to the right and the blue point to move 2 steps to the left, and the pink point here also moves 4 steps to the left, which it can in 2 seconds because this point has a maximum velocity of 2. This also tells you that anything less than 2 seconds will not suffice. So even if you have 0.9999 seconds at your disposal, the green and the blue points will still fall slightly short of meeting. This is also a good opportunity for me to point out that the answer in terms of the number of seconds also need not be an integer. So we are really looking at 10 to the minus 6 level of precision here. Again, this will become clear when we start getting to the implementation later in this video. But for now, just keep that at the back of your mind. The number of seconds that you report need not be an integer. So with this example fully worked out and behind us, let's now address the more general question of whether it's possible to meet within k seconds. So if I tell you that you have a budget of k seconds and you have all this information about the starting points of all the n friends and their respective maximum velocities, can you figure out if it's possible to get them to meet within k seconds? Now, based on the way we tackled the example, you might already have some thoughts about this. In particular, because we know the initial locations and we also know the maximum velocities, we also know how much people can move within k seconds. So we could draw out these intervals around each of these points, realizing that anything outside of this is not attainable within k seconds. Now, based on this, can you come up with a criteria for whether people can meet within k seconds or not? Take a moment here to think through this, because this is one of the key pieces of the puzzle, and there's one more coming up that has to do with the theme of this lecture, which is binary searching, but we'll get to that in just a few minutes. For now, just think about how will you figure out if k seconds is enough for people to meet. Okay, so I guess it's reasonably clear, at least visually, that it's possible for everybody to meet within k seconds if and only if there is a point that belongs to all of these intervals that we have drawn here. In particular, for this example, notice that it's not possible for everybody to meet because, for instance, the pink point and the orange point are always going to be divorced from each other. They're never going to come to a common place, at least within this time, assuming that these intervals are an accurate representation of how much they can move based on their velocities. On the other hand, let's look at an example where things do work out. So for instance, if the intervals were positioned like this, notice that there is at least one point. In fact, there's an entire range which could be used as a meeting place, because the points on that range are accessible to all people involved here. So that brings up the natural question of how can we figure out if a collection of intervals has a common point or not. This is again a cute question. If you have a collection of intervals given by their left and right endpoints, what would be an algorithm to figure out if there is a point on the line which is contained in all of these intervals? Again, just take a moment here to think through this and see if you can work it out, and come back once you're ready. Okay, so hopefully you had a chance to think about this. Let's go back to the example from before, and here let me highlight all the left endpoints of all the intervals, and one of these is special. The one that is special is encircled in red, and this is among all the left endpoints, it's the rightmost one. Let's also highlight all the right endpoints, and here the one that I'm interested in is the leftmost of them. So the two encircled points are the leftmost of the right endpoints and the rightmost of the left endpoints. And the criteria for all the intervals to overlap is simply the following. What we want is for the rightmost of the left endpoints to come before the leftmost of the right endpoints. If this happens, then you know that essentially everybody meets within this range that is defined by these 2 points. But if these 2 points are separated as they are in this picture, then things don't quite work out. So let's also see an example of when things do work out. So for instance, here you can see that the rightmost of the left endpoints comes first and the leftmost of the right endpoints comes afterwards. So this works out nicely, and you can see that there is a substantial range of potential meeting points in this example. Now this is a statement that you can actually prove formally. So let me just write out the criteria here. So if you have that the maximum of the LIs is at most the minimum of the RIs, then you do have a meeting point, and in fact every point in this range, max LI, min RI, will actually give you a valid meeting point. And the reason for this is, well, suppose that there was one interval that was outside of this range, it did not intersect this range, then depending on whether the interval was to the right of this range or entirely to the left of this range, you can argue that either its right or left endpoint will contradict our definition of the choices of min and max. So this is a really simple 2-line proof, and I would encourage you to write it out if you're not completely convinced already. The other side of the argument, of course, is that if this does not work out, so in particular, if the max of Li is greater than the min of Ri, then if you just look at those two intervals, right, the ones that witness this max and min, you will see that those two intervals themselves are disjoint, and therefore there is no hope for these two intervals to intersect, and therefore it's certainly true that all of the intervals don't have a common point on which they overlap. So this is the criteria that helps us determine if k seconds are enough or not for everybody to meet. But now notice that our actual task is to find the smallest k for which a meeting is feasible. So how do we go about that? This is where the binary search comes in. So once again, let's go back to this question here. So we know how to address this question. Given k and given all the xi's and the vi's, we know how to figure out whether k is enough or not. By the way, hopefully it's clear by now that the xi's are the locations and the vi's are the max velocities. Okay, so we know how to figure this out, but notice also the following two things. First of all, if the answer to this question turns out to be no, right, so k seconds are not enough, then certainly anything less than k is also not enough, because already with k you are not able to meet. So if you have even less than k seconds at your hands, then you're even more constrained. So of course it's not going to work out, because if it worked out with less than k, then it's going to work out with k as well. Right? So hopefully it's clear that if the answer to this question is no for some k, then it's also no for every value that is less than k. Similarly, if the answer to this question is yes, then the answer is yes for all values that are bigger than k. So that means that if, let's say, 5 seconds was enough, then of course 6 seconds are also enough, and 7 seconds are enough, and so on. So once you have a k that is feasible, the interesting question is, can we do it with smaller k? Right? That's what we want to figure out. And if you have a k that is infeasible, then the question you ask yourself is, okay, so k was not enough. We probably need to give ourselves a little more budget, a little more wiggle room. So that motivates a very natural binary search over the range of all possible k. So based on the limits of the problem statement, let's work with the range 0 to some large number. I think something like 10 raised to 9 or so should suffice. And with this range, we're binary searching, so we start in the middle, and we ask ourselves, is 50 how many ever seconds enough, right? And suppose the answer turns out to be yes, that this is enough, right? Then what should we do? We want to throw away half of this range. Which half should we throw away? Just think about that for a second, and pause the video if you need to, especially if this went too fast. Then just really take a moment here to think through this, because this is the crux of the binary search part of the algorithm. Okay, so hopefully you had a chance to, commit to an answer. So if, these many seconds are enough, then we need to challenge ourselves to see if we can do it with even fewer seconds. So we don't need to worry about the right half of the range, it's only the left half that's relevant. So we bring the right endpoint of our, search space down to the midpoint. On the other hand, if the answer is that it was not feasible, then perhaps you can anticipate that the interesting range is the right half, because if it's not feasible, we know that anything smaller is also not going to be feasible, so there's no point in checking for those numbers. So we search in the right half, and in other words, the way we truncate our search space is by bringing the left endpoint to the middle. That's kind of how you would do it in the program. So that completes essentially the overall description of the algorithm. You binary search over all possible values that the number of seconds could take, which is the answer. And every time you pose a question, is so many seconds enough, you use the interval intersecting business that we discussed a few minutes ago to figure out whether the answer to the question is yes or no. And every time you have an answer, you know which way to proceed, right? So hopefully by now you have enough information to try and implement this algorithm yourself. So please go ahead and give it a shot. Do keep in mind that the numbers can be big, and the answer is required to be within a 1/10⁶ error bound. So it's possible that the judge has a particular answer and you have a slightly different one because you're dealing with floating points, and some calculations may not be exact, but you want the difference between the answer of the judge and your answer, the absolute difference between them, to be within 10⁻⁶. So just make sure that you're using enough precision as you go along. So in particular, we're binary searching, right? So one way to think of the binary search criteria is, when have you narrowed in enough to say that you know the answer? So remember back when we were talking about the problem definition, we said that the output, which is the number of seconds, need not be an integer. So you certainly cannot just stop when you have a pair of consecutive integers, one of which reports yes and the other reports no, and then you just report the one that said yes. That's not enough. You have to dig deeper into the gap between these two consecutive integers. So for instance, suppose you say that 1 second is not enough, but 2 seconds is enough. You still have to probe the possibility that maybe 1.5 seconds are enough, right? And if the answer to that is yes, then you have to continue your search between 1 and 1.5. So when do you decide to give up? Because these are, well, since these are not integers, what is the stopping criteria going to be? Well, you have to decide when you have two numbers that are close enough for you to take a call. So you keep the search going for as long as the two numbers that you're working with are sufficiently far apart. And since you're looking at a 10⁻⁶ kind of precision, you can say that if the numbers are closer than that, then you can say that, okay, this is a good enough approximation of the final answer. So that's how we will be implementing it. And I think that's the spirit in which most of the implementations would be for this problem. So please go ahead and give it a shot, and come back to exchange notes as usual. I'll spend a few minutes in the rest of this video just going through my implementation for this. And for this problem, the implementation that I will show you is in Python. By now, by the way, we have an announcement which is on the mailing lists as well as in Discord, where we have shared with you a link to a Google form requesting for translations of the sample answers in other languages. So for instance, for this problem, the GitHub repository will already have the Python code. By the time you're watching this video, this should be up. But it'll be great if you have a C++ version or a C version or a Java version of the same code, as long as you follow a similar format and document your code well. And if your code passes all the test cases, then please do share it with us so that we can add it to the repository with full credit. So make sure you add your name and anything else that you want to add about yourself in the comments, and we'll be very happy to share this with the rest of the class. And thank you in advance for your contribution to making this course better. Okay, so with that said, let's move on to the implementation here. So the first few lines here are just, again, accepting the input. Again, nothing special here. The input is always just 3 lines. So the first line is the number of people. The next line is a space-separated list of integers, which talks about the locations. And the last line is a space-separated list of integers, which talks about the velocities. So you read them in, and I've used very short variable names here, but they're still descriptive. So X for the xi's and V for the vi's. So that's easy to remember, hopefully. Let's move along. Here is the criteria for determining if k seconds are enough. So we have 3 very short functions. The first one identifies the rightmost left endpoint. And remember, the left endpoints are given by the offsets from the original location towards the left for how much you can travel in t seconds. So you say xi minus vi times t. I think that's hopefully reasonably natural and easy to understand. On the other hand, we have how much can you move to the right. So that is xi plus vi times t. And so those are, that's an array that collects the right endpoints. And the second function here is simply returning the leftmost of the right endpoints. So remember, this was the max of li, min of ri expression that we had seen a couple of minutes ago. And the isFeasible function takes a number k, which represents the number of seconds that you have on your budget, and it tries to figure out by just comparing the leftmost right endpoint and the rightmost left endpoint whether this is workable or not. Okay, so notice that the 2 functions above take t as a parameter, which is the number of seconds that you have, and that's what we are passing to them when we are writing the isFeasible function. So this hopefully is just quite closely representative of what we had discussed a few minutes ago. So the only thing left to do now is the actual binary search. So we initialize our range. Remember, you could need as little as 0 seconds, just in case everyone's already on the same position to begin with. And I think if you study the limits, you'll see that you'll never need more than 10 to the 9. So that's what we have here for left and right. And as we discussed, we're going to keep searching for as long as the search range has not become really, really tiny. So as long as r minus l is bigger than some really small number, we're going to continue our search. I think we always maintain the invariant that r is at least l. So the absolute value here is not really necessary, but it's there anyway, so it doesn't hurt, but I think it's not required. So I'm not sure why I added that, but anyway, so that's the criteria for whether you want to keep searching or not. So as long as R and L are sufficiently separated, you keep going. And what do you do when you're binary searching? Of course, the first step is to find the midpoint of your current search range. So that's the value of mid. And based on whether the current mid is feasible or not, you decide to truncate your search interval one way or the other. So remember, we said that if the answer is yes, if it's feasible, then we ignore everything, every number that is larger. We want to challenge ourselves to find a smaller number. So we bring R down to mid. On the other hand, if it's not feasible, we know that what we have is not enough. So we need to go higher. So we ignore everything that's smaller. And the way to do that is to bring the left endpoint all the way up to the midpoint. So that's how we reset the values of L and R, and you just keep going until you have a search range that is sufficiently tiny. At that point, you can exit the loop and print the answer. So this is, I think, fairly clean and in some sense also a little bit clever. I think at least this solution wasn't completely obvious to me. I think the part about the intervals, I think, is pretty natural to do, but from there you start thinking about whether you want to do something that's greedy or something else. But the final solution that does happen to work, I think, is really cute, and I hope you enjoyed this as much as I did. So with that, we call it a wrap here, and we'll see another problem in the next video as usual. So I'll see you there, and in the meantime, thanks for watching.